Hey guys, welcome to this recorded class. As you know, we were not able to have our regular meeting on Friday. I think it was the 20th. So yeah, January 20th, and that is why I am recording this class, this video. But since the idea is that in this upcoming week, we continue with our subject, which is going to be actually the application of what we are going to discuss in this video here. Okay, so as you might remember, last class we were talking about base conversion. So converting from, let's say, binary to decimals, decimals to binary. But we did not actually we didn't discuss anything about hexadecimal. So that is the goal here today. But just to recap, as we already talked about, this is how we can convert decimal to binary to decimal. So if you imagine that you have this binary value here, 101.101. So we have to remember that we are starting in this position right here, the unit digit, right? The unit digit, not the hundreds digit, not the thousand digits, not the decimal digits. So we start with this one, considering that since we're converting from binary to decimal, so it's binary, this value here is in binary, therefore you have two possibilities, and you start powering the base with 0. As you progress to the left, you increase the power, so from 0 to 1 in this position, from 1 to 2 in this position. Now from the unit digit, if you move to the right, then you are deducting. So instead of 0, now the power is going to be -1, then the power is going to be -2, the power is going to be -3. So you have these values here, so therefore 2 power 2, that's 4, 2 power 1, that's 2, 2 power 0, that's 1, 2 minus 1, that's half, 2 minus 2, that's a quarter, 2 minus 3, that's 1/8. Now the digits that do have one value will be the ones that you are going to sum up. So I have 1 in the position that represents 4 in decimal. So 4 plus, then I have 1 here in the digit position that represents the decimal 1. I have 1 here in the binary position, the digit binary position that represents a half, and then 0. Therefore, I move forward to the right. The next digit that has value 1 is in this position that corresponds in decimal to 1/8. I'm going to sum up these values here. Therefore, this is what you're going to get, as you might remember from last class. Okay, now moving forward, in order to do the opposite, convert from decimal to binary, it's actually pretty straightforward, pretty simple. All that you need to do is to get the decimal value that you want to convert to binary and divide it by 2, because it's a decimal value. So it's base 10, and you want to convert it to base 2. Therefore, you're going to divide your base 10 value by the base that you want to convert to, which is binary. Therefore, the value is 2. So 92 divided by 2, you're going to have a quotient of 48, and this is what actually matters, is the remainder. So you need to write down the remainder. Okay, so keep moving. If the quotient is 48, then you're going to divide 48 by 2, that's 24. Write down the remainder. Well, 48 divided by 2 is 24 without any remainder, or the remainder is 0, if you will. Therefore, you have that 0 here. Now 24 divided by 2, that's 12. Remainder 0, then 12 divided by 2, that's 6. Observe that we're writing down the remainders. 6 divided by 2, that's 3. 3 divided by 2, that's 1, and you have 1 as a remainder. And and then 1 divided by 2, that's 0. You also have remainder 1. Now, what you're going to do is, a mistake that some people do is that they try to convert from decimal to binary by simply taking the remainders in this sequence, the sequence that they divided. You should do the opposite. Okay, so you go from, in this case here, since we're writing it down line by line, we go from bottom to top. It's not from top to bottom. So if you observe the binary number here, so 97 in binary is going to be 1, 1, 0, 0, 0, 0, 1, as you can see over here. Now, obviously, if you memorize these values here, you can simply subtract according to the nearest value. But this is not the goal here is not to focus too much on this. If you do want to take a look at this other possibility of conversion from decimal to binary, please come to me, talk to me, and I'll show you. Okay, now what actually matters to us is hexadecimal number system. Okay, so each digit could have a value from 0 to 15, which means 16 different values. This is why it's called hexadecimal. So again, if we're talking about a binary number system, binary means that you have 2 possibilities. A decimal system means that you have 10 possibilities. Therefore, a hexadecimal system means that you have 16 possible values, ranging from 0 to 15. Now, the difference is that it is not actually represented by, so you're not actually using 2 digits to represent the numbers, the values that are above 9. So what I'm saying is, in hexadecimal, it doesn't go from 0 to 15 actually. It goes from 0 to F. So it goes from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it goes to A, B, C, D, E, F. F meaning in decimal, as we know, meaning 15. But again, it's not actually 15, it's F. It's not actually 10, it's A. So the number system is base 16. It is easier to work with hexadecimal values than decimal or binary because one hexadecimal digit is represented by 4 bits, 2 hexadecimal digits are represented by 8 bits, which means 1 byte. So if we consider that in IT, we're mostly working with bits and bytes, right? And considering that a byte means 8 bits, it is easier to use a base system, a number base system, in which that is actually multiple of 8, right? And you could also think about binary values. That it would also work. But the problem is that if you use binary values, you're going to have such long numbers. So if you use hexadecimals, you can reduce the length of your number and still use that value to represent a byte, for example. So this makes conversion between hexadecimal and binary very easy because, again, a hexadecimal value is composed of 16 possibilities, whereas a binary value is composed of 2. So they're multiple, right? Which means that you're going to see that the conversion is pretty simple because if you look at first of all, again, this is the conversion between decimal and hexadecimal. Now, if you look at how to convert a binary value to hexadecimal, and you're going to see that the opposite is also pretty straightforward. You're going to realize that considering that a hexadecimal is composed of 16 possibilities, 16 values, different values, and a binary value is composed of two possibilities, two possible numbers. Well, since they are multiple, you can basically divide the binary number into groups, each group having 4 bits. So if necessary, you can add the zeros to the left to make a complete 4-bit group, or to make complete 4-bit groups. So convert each 4-bit binary group into its hexadecimal value. Again, if 8 can be divided by 2, I can combine these binary possibilities into 4 to reach the value that I am talking about. And that is because 4 bits will give you the possibility, will give you 16 possible different values, right? So basically what you can do is, for example, let's say that you want to convert 1101011011. You're going to divide it. Now, this is important. You have to divide this value into groups of 4 bits, but going from the right to the left. So the first group would be this group here, which is right here, 1011. The second group would be 1010 right here. And the third group would be that one that was left alone. Now observe that if I'm considering that I'm converting groups of 4 digits, then I will need to complete to the left with zeros. Complete the group of 4 digits with 3 zeros to the left. Obviously, they have to go on the left because zeros on the left do not change your value, the value, as you know. So this is what you're going to get. Now, what you can do simply is to convert those groups of 4 into a hexadecimal value, right? So now you might be asking, why groups of 4? Well, because 2 power 4 means 16, which is the number of possibilities that we have in a hexadecimal base, in a hexadecimal number system, right? So that is why the combination of 4 bits will give you all the possibilities in a hexadecimal, right? So for example, if we scroll down and we take a look at the this table here, which I'll get there soon, but if you look at the binary values and the hexadecimal values here, you're going to see that, for example, 0 in binary, which corresponds to 4 zeros, correct? 0, 0, 0, 0, that means hexadecimal 0. Now 1, meaning 0, 0, 0, 1, that corresponds to 1. Now 0, 0, 1, 0 corresponds to 2, 0, 0, 1, 1, that's 3, 0, 1, 0, 0, that's 4, 0, 1, 0, 1, that's 5, 0, 1, 1, 0, that's 6, 0, so forth, so on, until you have all the possible combinations with 4 digits that will lead you to hexadecimal F. So those are the possible combinations, right? If you go down to this table here, okay, this is a table just to facilitate, just to help you figure this out. So if you go to that table, you're going to see that 1011, that means B, 1010 means A, and 1 or 0001 means 1. Therefore, this binary value here in hexadecimal is 1AB, right? Therefore, it is 1AB. Now, you can simply do the opposite to convert from hexadecimal to binary, obviously, right? So you convert each digit to its 4-bit binary value. So again, if we go down to that table, oops, I'm sorry. if we scroll down to this table, we can basically do the opposite. So if it's 1AB, what is 1? Oh, 1 is 1. What is A? A is 1010 and B is 1011. Therefore, that is going to be 1AB in binary. 1 1 0 1 0 1 0 1 1, as we see right here. So it is much easier to work with large numbers using hexadecimal values than decimal or binary, as I mentioned. One hexadecimal digit means 4 bits, two hexadecimal digits means 8 bits, and 8 bits is 1 byte, again, as I mentioned. And there's the table. In this ASC table here, you can actually see the conversions or the translations or associations for all these 4 different number systems: decimal, hexadecimal, binary, and octal. But not only that, you also have the character representation here. That is because, well, for example, we use a keyboard to write stuff, right? But as you know, a computer does not know what the character A is. It doesn't know what the decimal number 100 is, right? It only speaks computer language or assembly language. So what actually works for the computer is binaries and hexadecimals. Oh, but it depends on if it's assembly language, it's using hexadecimal. If it's instructions, then signal, as far as signal, you have binary values. But the important thing here is that the computer doesn't understand the characters as we do. Therefore, we have that table of association, right? So for all the zeroed number systems, that means the character no. Now, for all the other possibilities that you have in your keyboard, you also have a corresponding code in each number system, right? That is why we also have symbols, the possibility of using symbols. They correspond to a specific number system value, right? And if you observe, the number of possibilities here is 127, which is actually from 0 to 127, which means 128 possible values. If you think about it, 128, that's base 2, so that's 2 power 7, okay? And that's how the ASC system works. It will give you, it supports 2 power 7 possibilities. Actually, it supports 2 power 8, but by default, you use 2 power 7. So, but because of the evolution of technology, they saw the requirement for a different table system. That's when they created UTF-8, which is used in HTML and it has the same byte values as ASC or ESC if you prefer, with the difference that UTF-8 not only supports 2 power 8 possibilities, but that's the default. By default, it has 2 power 8 possibilities. Whereas UTF-16 is used in environments that balance efficient access to characters with economical applications. So recent versions of Microsoft Windows, for example, use UTF-16 encoding. Each character is encoded in 16 bits. Now, it does support, so UTF-16 does support UTF-8 and ESC, but it just has a wider range of possibilities, which means that it's basically just filling those possible digits with 0. Now, why is it so important to understand base conversion? Well, like I said, because since we are now starting to take a look at malware conversion, malware analysis should be done basically analyzing instructions. And when it comes to instructions, we're looking at assembly language. Now, that is because, again, the computer will send instructions using computer language, assembly language. Well, so we have to understand hexadecimal. And in order to get there, in order to understand instructions and hexadecimal values, we have to be able to perform those base conversions. Okay? Now, on top of that, there are some other tools or technologies or resources that are also very important for malware analysis. And one of those, which also will require you to understand hexadecimal values, right? So as you know, and as you can see, whatever we're going to study, it's stackable, it's overlapping, the subjects are interdependent. You cannot just jump to, let's say, week 7 without understanding what we've studied in the previous weeks. Okay, so therefore, another very important topic, and this is what we'll start focusing on for our malware analysis process, is understanding hash values. Okay, so let's take a look at, let's have an overview of hash value and its application. I'm sorry. So, fingerprint and hash value. The idea is pretty much the same, at least for malware analysis, right? A fingerprint is an image or a sequence and information that will show you that, well, if I understand and I assume that there is no two different people that will have the same fingerprint. And obviously, we're not going to discuss twins, twin brothers, twin siblings, and none of that. But let's just assume, okay, this is an assumption, that two different people, they do not have the same fingerprint. Well, that means that if I can identify, if I can get a database, create a database with the fingerprint of everybody in the planet, I should be able to identify and tell apart different people. It's the same thing with hash values. The idea is that an information will always generate a different hash value if I compute the hash value of a specific input. So that's the idea. Therefore, if we take a look, so for example, if we read this message here, there is $1,500 in the blue box, right? Now, observe that I am including letter X in this hash here. So there is 1500 in the blue box, including X. This is the hash value that I am generating, right? Now, if I take this message here, there is $1,500 in the blue box. The hash that is generated here should be different. It should be different, okay? Now, how different, how much different, that doesn't matter. It doesn't matter, okay? What matters is it is different. And it doesn't have anything to do with the original message in such a way that even if I get a hold of the hashed value, I cannot go back to the original message. So this is why it's important to understand that hashing is not encryption, although encryption algorithms usually do use hashing, but this is not the same thing. Encryption means that you have a key, or it can be a pair of keys, but there is a secret that will allow you to get a hold of a specific message, a clear text message, for example, and you're going to scramble that message in such a way to generate a scrambled message. Now, if another person has the right key, that person should be able to have an access to the scrambled message. That person should be able to go back to the original message to read it. This is not how it works with hashing. When you generate a hash value of a message, if someone gets access to that hashed value, that person should not be able to go back to the original message. Okay? So, hash functions produce a fixed length output, usually 128 bits, form a message of any length. Well, actually, it's from a message of any length. So this is also very important. Keep in mind that if the input message or the clear text message or the original message that I want to hash is, let's say, 10 characters long, the result of that hash will be, it will generate a hash of 128 bits. If I get another message that has 100 characters, the result will be just the same. Well, not the same hash, but the same length. So the length of the resulting hashed value will be the same, 128 bits. So hashes are unique to the input or the message that produces them. And alerting just one bit, not alerting, I'm sorry. Well, actually, there's so much fix to be done to this slide. Altering just one bit of the input message will produce a noticeably different hash output, as you saw, right? Usually the result is going to be quite different. There is no way of recovering the original input message from the output hash value. The hash function is a one-way function. One-way function is a function that is easy to compute output in one direction, but it is very difficult to compute the input data from the output. So as you can see, I have an input here. I apply my hashing algorithm to that original information. So age, capital H X here is the function or the algorithm, if you prefer, being applied to that original message of any value. It will generate a hash value with a fixed length that can be, well, basically it can range. It will depend, again, on the algorithm that you are using. Okay? Now, as far as hashing algorithms, there are many hashing algorithms such as MD2, MD4, MD5, and secure hash algorithms, which is represented by SHA, if you prefer, or SHA. MD2 produces a hash value of 128 bits long. It is secure but very slow, which means that, well, especially for nowadays, with performance being such a critical metric, MD2 doesn't work. MD4 is faster than MD2 and simple to use. It uses 3 processing rounds to produce a hash of 128 bits long. However, it was subject to successful attacks, which means, okay, it's faster, but it's not secure. Whereas MD5 was developed from MD4 and to be more secure than MD4. It uses 4 processing rounds to produce a hash of 128 bits long. So basically it uses 1 processing round more than MD4, and MD5 hashing algorithm is used frequently on routers, servers, and computers. It is susceptible to collision attacks, which means that It is safer than the previous ones, but it is also a node algorithm. So it's fast, it's safer than the other ones that we're discussing, but it is still susceptible to collision attacks specifically. That is why the most secure hashing algorithm is the secure hash algorithm SHA or SHA, which was developed by NIST. SHA, so you have the different versions for all those algorithms. Specifically for SHA or SHA, started with SHA-1 that produces a hash value of 160 bits by 4 processing rounds. Therefore, similar to MD5, 4 processing rounds. However, you have an output or a hashed value longer than the one generated by MD5. SHA-1 is employed in several widely used security applications and protocols, including TLS, SSL, PGP, SSH, MIME, and IPsec. SHA-1 was cracked in 2007 by Professor Xiong Wang and her associates in Tsinghua University and Shandong University of Technology. Several vendors such as Microsoft, Google tried to move from SHA-1 to SHA-2, and they actually selected SHA-2 in 2012. So SHA-2 has 3 versions: SHA-256, SHA-384, and SHA-512 algorithms. They were designed to be used with the AES encryption standard, which is currently still the encryption standard defined by NSA and NIST. Now, again, the application of hash function. Why are we talking so much about this? Because we have to do malware identification. So we can use hashing to deploy a malware identifier. That is actually how malware identifiers work, and I talked a little bit about this in class, right? Based on signature. And this signature is generated by the computation of a hash value. So that is how virus scan softwares work. You can also use it to protect password information. You can use it for software authenticity, data integrity for stored files. You can provide data integrity for public encryption. As I mentioned, the combination of encryption and hashing. You can implement keyed hash for message authentication, such as MAC. And you can also perform digital signatures by signing the original message instead of encrypting that message. Now, what matters to us is using hash to identify malware. So what we want to do is to run a hashing function such as MD5 against the malware code in order to get the malware hash or fingerprint, if you will, that identifies the malware. Again, that's basically how anti-malware softwares work, right? So let's say that you can identify a file or a code as a malware. Well, what you can do from there on is to compute the hash value of that malware code and then include it in your database of malwares. Again, that's how anti-malware softwares work, right? And you can also do that to verify if you have, instead of generating the signature, you can compare a pre-existing signature with a code that you have. So you can do it by yourself by basically saying, hey, I believe that this might be a virus file. This might be an infected file. Compute the hash value of that file and compare it with a database of signatures or hashes that you have. Right? Again, that is how virus scan softwares work. And that is why you should always update the virus database regularly to include the hash values of new viruses. And we should actually increase this to malwares, not just viruses. Okay? So on Monday, we are going to start to get our hands dirty by doing some labs. So we're going to deploy some tools. We're going to take a look at how we can actually use hashing to favor us, how we can leverage hashing into identify malware codes. I hope you enjoyed this class, guys, and thank you very much.